Asteroids, remnants from the birth of our solar system. From planetoid-sized monsters down to tiny pebbles, they have orbited our sun for billions of years. We have seen some up close, even touched their surface. We count their numbers, chart their courses, and keep a wary eye on these mountains in the dark. Several spacecraft have ventured out towards these rocky worlds. Some have touched down and taken samples with surprising results, then returned them to Earth. Scientists have found these remnants to be complex and full of secrets. There are different types of asteroids, and 2 new robotic probes are ready to study some of these unique targets. One is called Psyche, and it is perhaps one of the most interesting.
Psyche is an asteroid that orbits the sun out between Mars and Jupiter. It's called Psyche because it was the 16th asteroid discovered, and they were all being named after gods and goddesses at that time.
So the Psyche mission is going to visit an asteroid which is called Psyche. And it is a large metal asteroid, a unique body in the solar system, 150 miles in diameter approximately, and made of 40 to 60% iron nickel metal. That makes it a unique body in the solar system. We visited worlds made of ice and worlds made of rock and worlds made of gas before, but we've never visited a metal world. So we'll get to see something unique and different for the first time.
All the rocky planets that we know of, the Earth, Mercury, Venus, Mars, and the Moon, all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field, which may be tied to holding onto our atmosphere and making our planet habitable. There's a lot of study that's going on to understand that. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there. And so Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And so we hope to learn something about what's inside the Earth and other rocky planets by visiting Psyche. But it also tells us about the processes in the very beginning of the solar system. It helps us understand how planets form in the first place.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma-ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma-ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma-ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the MESSENGER instrument.
That technology that we developed for the MESSENGER spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can take what we learned from the prior missions and implement it now and make an even better instrument.
Only one body like this that's this big and made of metal in the solar system. So the big mystery is, where did it come from? How was it created? One of the theories about it is that it was once the inside of a forming planet, because the planets that we know, Earth, Mars, Venus, Jupiter, have metal cores inside of them. So this may have been the metal core that was forming inside of a baby planet, which then collided with other planets that stripped off, forming planets that stripped off that rocky mantle, just leaving a piece of that core in space. And if that's the case, then by studying this body, we'll be able to study the cores of planets like our own, the Earth, in a way that we could never do otherwise.
Psyche is a large asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber and use it as a target for our input experiment. And we were shooting quartz bead at high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great detail. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place, and this is because the metal is much harder than rocks, and so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data, and there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
There is nothing like the experience of sitting on console on launch day and hearing all the people go around and say, we're go for launch, and then finally getting to say yourself, we are go for launch. It's the culmination of all those years of effort and all those hundreds of people working, and so it's super exciting when you actually, finally say, we're go, and we're gonna get that beast into space. We're going to go launch and do a Mars gravity assist, go by planet Mars, and then continue on to the asteroid using electric propulsion.
I think no matter what we think it is right now and how much we hypothesize what it might look like, I think it's going to really surprise us and change our views about our solar system when we get there. And it's an incredible opportunity to be a part of the team making that happen.
The Psyche mission has suffered several launch delays. However, it should be underway in the next year or two.
Three, 2, 1, 0. Liftoff. Atlas V takes flight.
Another ambitious mission that has launched is Lucy, to study several asteroid targets.
Tower clear.
So Lucy is going to survey 8 asteroids over a 12-year mission life. The first asteroid is in the main belt asteroids. It's Donald Johanson. And then the remaining asteroids are the ones that we call the Trojans. And because we believe that they are remnants of our solar system, by studying their geology, as well as their composition and their mass, then that will give us insight into planets, planet formations, and in particular, the outer planets.
The Trojan asteroids, which are located in these Goldilocks zones of gravity-stable orbits or in between the Sun and Jupiter, are really leftover fossils from the formation of the solar system. And these fossils are around 4 billion years old, and when the solar system was forming, they were brought into these locations. And the Trojan asteroids, which have been there since the formation of the solar system, are these last unexplored remnants from the cosmic neighborhood creation. And we're extremely excited to go and visit them because of our total lack of understanding of exactly what is out there. And so it's going to be extremely exciting when the Lucy spacecraft explores them.
Some of the most important planetary science questions we're trying to answer are focused on the origin and the evolution of the solar system. Asteroids and other small bodies are really important keys to understanding that history. Amazingly, many of these mysterious worlds have been altered very little in the 4.6 billion years since they first formed. Their relatively pristine state makes comets, asteroids, and some meteorites wonderful storytellers that have preserved clues they can share with us about conditions in the early solar system. In particular, by studying the Trojan asteroids, we can gain more insight into the history of the outer solar system and the giant planets, Jupiter, Saturn, Uranus, and Neptune.
The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else.
After launch, the Lucy probe failed to lock one of its solar panels in place. Engineers are working on a resolution to this problem.
The Lucy spacecraft will travel 4 billion miles over its mission. And it is a very sophisticated, well-orchestrated trajectory that gets us there.
I cannot wait for those gorgeous images that our instruments are going to take and bring back to Earth. What that's going to tell me and the world is how gorgeous these objects are, what secrets they have to hold, and it's going to start us unlocking these mysteries of the solar system that are out there. I can't wait, and words can't describe just how excited I am to share with everyone these images when they first come back.
This animation is drawn from the recent data release of the ESA Gaia satellite. It reveals the locations of the larger asteroids within our solar system. This tapestry of orbits shows that several near-Earth objects cross our orbital plane. Geological history records that some have hit the Earth with devastating effects.
We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the two asteroids in the Didymos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
And we understand where about 40% of those asteroids are. We know that no known asteroid is a danger to the Earth right now, but the concern is about the asteroids we don't know about yet. And if we should ever discover an asteroid that's on a collision course with Earth, we want to be able to discover this years in advance so we can give the asteroid a push, not to destroy it, we probably wouldn't be able to do that anyway, but just to prevent that collision. And the DART mission, the Double Asteroid Redirection Test, is our first test of one way of doing that.
Launched aboard a SpaceX Falcon rocket, DART is well on its way to its target.
So the way an ion thruster works is that it utilizes electrical energy to ionize propellant and accelerate it using electric and magnetic fields. What NEXT does is that it increases the power level, you get more thrust out of it, it's more fuel efficient, it lasts longer, basically kind of improves things in almost every way and makes it very beneficial for end users to utilize.
When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch.
DART's going to a binary asteroid, a double asteroid, for two really good reasons. The little asteroid, Dimorphos, which is in orbit around the big asteroid, Didymos, that asteroid is about the size of object that we would tend to be concerned about. The most abundant asteroids are the small ones, and this one, about 160 meters across, or about the size of a football stadium, is large enough that it really would cause severe damage if it struck the Earth. Now, by doing our experiment, a kinetic impact experiment on the small moonlet asteroid, we're able to measure our effectiveness in deflecting the asteroid by watching the change in the orbit of the little asteroid around the big one. It makes that measurement a lot more precise and a lot easier to do with telescopes on Earth. The other reason we're doing it is that the presence of the large asteroid there keeps the little one in orbit around it as the pair go around the sun. So that means that this asteroid, which is not a danger to Earth now, will never become a danger to the Earth because of anything that we do in the DART mission. DART is carrying a small CubeSat. It's called the Licia Cube. It was contributed by the Italian Space Agency, and its job basically is to watch the impact from a little distance away. It's riding along on the DART spacecraft, and it's going to be deployed a few days before the kinetic impact. It's going to maneuver and offset itself to the side so that it doesn't run into the same asteroid that DART is running into, and it's got two cameras on it that are going to try to first catch the actual impact of DART on camera, but then more importantly, see the ejecta, the plume of material that's blown off the surface of the asteroid and how that develops. If we're fortunate, we'll be able to see the impact crater newly formed by the DART impact, And then, of course, LiCHA-Cube is going to do something that DART can't do, that is fly past the asteroid, look back, and get the full three-dimensional shape of the object that we hit, which we won't know until we actually get there.
One other threat to Earth is the interstellar object passing through our solar system. They arrive without warning, fast-moving and having no known orbit. Another hazardous mountain in the dark.